Hi everybody, welcome back. We are starting a new chapter on work and energy, specifically kinetic energy, but we'll get more into that a little bit later. And this is going to be chapter 8 in our Physics 1 class. So let's just go ahead and get started by defining what energy is. Energy, well, you can define it a lot of ways, but you can think of it as being the state of an object. For example, it has energy as a result of its state. Is it moving at high speeds or any speed? Is it at rest in a precarious location? It may have some kind of energy. And we'll talk about work a little bit later on, but you can think of energy as the ability to do work, to carry out some sort of process. Energy can be transferred from point A to point B or from object A to object B. We're going to be talking about different kinds of energy. In this class, mechanical energy is what we're going to focus on. We're going to talk about kinetic, that is the energy of motion, and potential energy, that is the energy that an object has as a result of its position. For example, this right here, we have this guy, and it's a fine color, standing right there, and this bowling ball above his head has energy. It has a potential to do what? Well, it has a potential to fall down on because the bowling ball has been raised up against gravity and energy has been put into it. We call it potential. But kinetic energy, of course, is the energy of motion, things that are moving. And moving objects have the ability to do work just as much as an object has the potential to do work, like a bowling ball. In contrast to mechanical energy, which is what we're going to talk about, you can think of energy being like, say, chemical energy. That is, chemical energy is wrapped up in molecules that have the ability to burn. But we're not going to be talking about that. We're going to be talking mostly about mechanical energy, especially kinetic and potential. Okay, so we said just a minute ago that energy is the ability to do work. And both of them are really measured in the same units. That unit is the joule, Joule. But before we go into kind of talking about what a joule is, let's define work a little bit better. You can say that work is the amount of energy that is given to or taken from an object or a system. For example, let's say that you have a falling bowling ball, okay, and it has energy. It has, I'll put our little dots on it right there. It has kinetic energy, and that bowling ball is able to take its energy and do work and apply it into crunching up a soda can when it crushes on it. All right, so that's a soda can right there. We can say that work has been done to that soda can. So energy was taken out of the bowling ball and used to do work on crunching that empty soda can. So maybe that helps you kind of understand how energy is either put in to a system or taken out of a system as a result of work being done. So we say that if you add energy to a system, that positive work is done. For example, if I were to put energy into this bowling ball by raising it back up, all right, it has more energy and now it can do more work. Conversely, if energy is taken out of a system, that is, if work is done to this soda can right here so that the bowling ball stops moving, well, we say that work is negative. So there's negative work done to the bowling ball. There is positive work done to the can right here. So really, energy is just kind of moved around the system from point A to point B. It's never really, well, according to Newtonian physics that we're going to talk about, energy is neither really destroyed or created, but it's changed forms. And you may have heard that before as well. But that kind of goes along with our whole concept of work and energy being two sides of the same coin. Now, I said before that work and energy are measured in a unit called joules. And 1 joule is 1 kilogram meter squared per second squared. All right, now that sounds like a big kilogram times meter squared per second squared. A big kind of convoluted unit, but what does that mean? Well, it really means that work, which is measured in joules, is really nothing more than a force applied over a distance. Or we could write delta x, I guess, for that, but we're just going to write our distance, or that is the amount of you might say displacement that the force is applied over. We're going to write that as d for now. All right, so if work is a force times a distance, well, what is a force? Well, a force is a Newton, but if we expand a Newton out, we know that a force is what force is mass times acceleration, right? So kilogram is mass, acceleration is meter per second squared, right? So this is really force, mass times acceleration. And if we multiply that by some distance m, or that is, well, some distance d, but distance is measured in meters, we have our kilogram meter squared per second squared. So really what a joule of work is a force applied over a distance. This is our force right here, mass times acceleration, and that's our distance, and that's how we get the concept of a joule, a kilogram meter squared per second squared. So this is a little more detailed, you might say, equation of what I just told you. Work being a result of a force applied over a distance. But the question is, what does this mean right here? Cosine of this funny symbol. Well, first of all, this symbol is phi, P-H-I. All right, it's another Greek letter. And it does represent an angle, as indicated by the cosine. I mean, you can't have a cosine of something other than an angle. This is an angle, but it's an angle between the force and the direction of displacement. First of all, this force should be constant. It can't be something that is changing, all right? So, like we talked about springs, springs force changes as you change your displacement. That doesn't work in this case. If you have a constant force, a constant push applied over a distance, work is done. But it's only done in the direction of motion. So, let's say you have a force. Okay, I'll just draw this like this right here. So we have a cart. All right, and that's the direction of motion, and it moves some distance d, right? This force is applied, let's see, I'll make this red, all right? So a force is applied like that right there, okay? Well, the force isn't moving a thing into the ground, it's being applied down right there. So there is an angle between the direction of the force and the direction of the motion. That's what phi is. So if here's our displacement, you might say axis, and here's our force, phi would be this right here. All right, so it's this, we might say it's the smaller of the two angles between the force and displacement vectors. This is the bigger of the two angles. We don't care about that. We care about the smaller of the two angles. So whatever is the angle that is, like I said, smaller, or you might say acute, between the force and displacement vectors, we call that phi, right there. So the next slide will hopefully flesh that out a little bit more for you. So let's say we have a force right here. Okay, oops, I'm not drawing. There we go. There's our force, and our force is displacing something in that direction, or, well, yeah, in that direction along that axis right there. Right, in this case, the force and the displacement vector, they are basically on the same axis. So that angle right there is, which is phi, is 0. So the force is being applied completely in the direction of motion. So we say the work done, that is force, times the distance, or the displacement of motion, times the cosine of 0. Well, what's a cosine of 0? It's 1. All right, and so all the forces are being applied in that direction of motion, and so you would have, you might say, your maximum work done. What if you have a force applied opposite the direction of motion? All right, so down at the bottom right here, so here's our force. All right, and here is our direction of motion, or our displacement right here. Okay, well, what's the angle between them? That angle is 180 degrees, right? That's 180 degree right there, so phi would equal 180. And so, what's a cosine of 180? Well, it's negative 1. All right, cosine of 80 is negative 1, and so really negative work is being done here because the force is being applied against the direction of motion, so negative work takes place, so That's why you'd have a negative sign in front. And there's every possible angle in between as well. So if the force is at some angle from the direction of displacement, whatever the cosine of that angle, phi, is, that would be what your multiplier is. So with this guy right here, all right, we have a force that is applied, and I should have made that red, I guess. Oh well. Just delete that. We have a force that's applied, and it's in the direction of motion, right? Our direction of motion is this D right there. So you could say he's putting all of his force into motion right there. If he were to be angling that force downwards, like that, well, you probably know from personal experience that that doesn't work very well, because only a certain component of your force is really moving that box. And also from the last chapter on friction and inclined planes, you also know that your downward force is increasing the friction, which makes it harder for you to work against that. So if you want to maximize your work, you put your force in the very direction of motion. But the force isn't always in the direction of motion. Let's say, for example, that you had a direction of motion that was, well, let's say you had an upward force. You were lifting something, okay? You were holding it up in the air. Say it's a box, something like that. But the direction of motion was at right angles. You may hear my dogs barking in the background. If you do, just ignore that. Was at right angles to the direction of the force right here. Okay, so you're lifting something up, you're applying a force to a box, but you're moving it that way. All right, well, let's ask ourselves, how much work is being done? Right here. Well, work is force times distance times the cosine of that angle phi. Well, what is that angle phi right there? That's 90 degrees. And the cosine of 90 degrees is 0. So work done equals 0 joules right here. Isn't that interesting? So you can apply a force up and walk sideways, and yet you will not be doing any work. So that's very much like if you were to lift a set of dumbbells and hold them over your head. It's tiring because you're holding them up, but if you're not lifting them through any displacement anymore, you're no longer doing any work. So this ant holding this box up is not doing any work, because this angle between the force and displacement is 90 degrees, and we all know that the cosine of 90 degrees is 0. So in order for you to be doing work, your force has to be applied at least in some way, some amount, in the direction that you are moving. Here's another example right here. This guy who is pulling his luggage through the airport. Here's his force. Horizontal is his direction of motion. Okay, and so this would be, now it's called theta right there, but we're going to call it phi for our purposes. So it's kind of like a sideways theta, or it's like a circle with a line through it. That is phi. So really only the horizontal component of his force is doing the work, because that's what's moving in the direction of motion. So here's the force. Here's the direction of motion. And this right there is our phi. If he were pulling straight up on that, vertically, but moving sideways, then you could say that there'd be no work being done in that direction, because there's no force applied in that direction right there. So that's why we say that work is always force times distance or displacement times the cosine of that angle phi. If that force and distance or displacement are on the exact same axis, well, that's great. The angle between them, phi, is 0, and the cosine of 0 is 1. But any other angle, you're going to have less effective force being applied, because not all that force is being applied in the direction of motion. Let's do one example, and then we'll wrap it up for this video, and we'll move to the next one. Or, well, we'll have a separate video. Okay, so here's example 8.1. Now, the first thing I'm going to do is make some space for us. I'm going to move this up a little bit. You should be able to read that, because it should be in your notes. All right, and we have an intern pushing a gurney. Now, a gurney is that thing that you lay on that has the wheels. All right, so it's a 72 kilogram patient on a 15 kilogram gurney. All right, so what's the mass of the system? Let's add them together, because that's going to be important. This whole system is being accelerated by this nurse right here. So that's 72 kilograms plus 15 kilograms, and that tells us that it should be 87 kilograms. All right. Producing an acceleration of 0.6 meters per second squared. All right. 0.6 meters per second squared. That's the acceleration. We're not given the force, but we're given the mass and we're given the acceleration. So the question is how much work is being done right here. All right. Oh, I forgot to add something. Sorry, I didn't write down all my givens, which we should do. It's being, that person is, the gurney, the whole system is being pushed through a distance, or displacement, you can call it that, of 2.5 meters. All right, so the question is, what is the work that is done by this nurse on this gurney patient system? Okay, well, let's write down what we know about work. Work equals a force applied over a distance times a cosine of the, oops, not theta, phi, right? Cosine of the angle between them. All right, well, what is that angle between them right there? What is the angle between the force that's applied and the direction of motion? Well, in this case, it's 0, right? There's no difference between the axis of the force and the axis of the motion. So that's 0 degrees, so that'll be handy for us. So we know what that will be, but we need to know what the force is. Okay, well, the force, we know from the last couple chapters, is mass times acceleration. So let's take the mass of the system, 87 kilograms, times the acceleration of the system, 0.6 meters per second squared. Okay, so that means our force is going to be equal to 52.2 newtons. 52.2 right there. All right, sorry about that. All right, so that's our force. The question is how much work is being done. Well, let's go back to our equation for work. Work equals force times distance times a cosine of phi. All right, well, we have everything right now, right? We have our force that the nurse is applying constantly to that patient is 52.2 newtons. Our displacement or distance is 2.5 meters. All right, and the cosine of phi right there is going to be equal to, or well, actually our phi, I should write that in, is 0. Cosine of 0 degrees is equal to 1. So if you were to key that in, if you were to key in 52.2 newtons, or 52.2 times 2.5 times a cosine of 0 being 1, then that means you should get a amount of work of 130.5 joules of work being done. All right, so she's really maximizing the work that is being done right here because she's applying her force in the direction that she wants to move. If you apply force in any other direction, you're going to be wasting some of your force, but the amount of force that she's applying over that distance is 130.5 joules. So that's your first example, example 8.1, and look for me on the next one. We're going to be getting into example 8.2. I'll see you then.